I start?
Dennis.
Yeah, so I'll just, yeah. So welcome everyone to the second meeting of the 26th Midwest Computability Seminar. Glad you're all able to make it. Very happy to have Verónica Becher here today to talk about normal numbers and perfect necklaces. Go for it.
Thank you, Dennis, for this invitation. In this talk, I'm going to talk about normal numbers and perfect necklaces, exactly. And at the end of the talk, I will make the connection with Martin-Löf random real numbers. I will make this connection further in the next talk I'm giving in 2 weeks in the Computability Theory and Application Seminar organized by Damir Dafarov and company. But today we start with plain normal numbers. So let b be an integer greater than or equal to 2, that we will call it a base. And we say that a real number is normal to base b if in its base b expansion, every block of digits occur with the same limiting frequency as every other block of the same length. For example, this number written in base 2 is not normal to base 2 because 0, 1, 0, 1, 0, 1 has far too many zeros. This other number, 0, 1, 0, 1, 0, 1, 0, 1, yes, it does have the same proportion of zeros and ones. However, it's not normal because the block of 2 zeros does not appear at all. In 1909, so more than 100 years ago, Borel gave this definition and proved that almost all real numbers are normal to all integer bases at the same time. And he asked for one example. All Martin-Löf real numbers are normal to every base, and that is very easy to see because one can construct a Martin-Löf test that includes all numbers that are not normal to some base. In particular, then, omega numbers are instances of normal numbers to every base. But Borel had in mind more explicit examples, and since he asked the question, a whole research program started, starting with Lebesgue in 1909, and Sierpinski. Early constructions were not even computable constructions, but there's a whole sequence of constructions. And in this talk, we are going to talk about 2 of them, Champernowne's construction and Mordechai-Levin construction, that are constructions of numbers that are normal to one base. It is not known whether they are normal to other bases for which the construction has not been devised. But in a strong sense, one can say that this research program is still open because Borel's question is essentially open. Borel would have liked to prove that the number pi or the square root of 2 or any of the mathematical constants were normal. And there is no yet enough understanding to prove that. So Champernowne proved that this number written in base 10, 0.1234567, and which is the concatenation of all natural numbers written in their natural order, is normal to base 10. Champernowne, called actually David Champernowne, was a student in King's College, Cambridge, and he was taking the number theory course guided by G.H. Hardy, and under his direction, he actually proved that this number is normal to base 10, answering to Borel's question. It was the intention. The technique used by Champernowne actually, although he does not say in his paper, appeared in 1887 already by Émile Barbier, who, look at the title of his article. It's actually 2 papers in the same volume. It assumes the concatenation of all natural numbers written in base 10, actually, and he asked, what is the digit that appears in the position 10 to the 1,000? And then the continuation is, what is the digit that appears in the position 10 to the 10,000. So here he develops the question on how many positions you need to write all the digits that require one position, all the digits that require two positions, all the digits that require three positions, and the concatenation of them. And then he wants to know exactly which digit appears in which position. So this is a probability. It is written in the area of probability theory, and it does a precise and careful counting for this combinatorial problem. So here is how Champernow's paper starts, 1933. He actually wants to prove that, or proves, the number 0.1, 2, 3, 4, 5, 6, 7, etc. is normal to base 10. And in order to do that, he first transforms the sequence into something simpler, which appears in theorem 1. He says, first, we shall prove, and it is the concatenation of all blocks of length 1, followed by the concatenation of all blocks of length 2, followed by the concatenation of all blocks of length 3, and so on. So for that sequence, he's going to prove that that sequence is actually normal to base 10. I'm currently interchanging between sequence of digits and actual number, because I'm assuming all the time that we are talking about the expansion of a real number written in a given base. I think we are all happy with this identification. So more precisely, in Champernow's proof, instead of talking about the actual, the first step is, instead of talking about the actual concatenation of all natural numbers in their natural order, we are going to talk about something simpler for us, which is the concatenation of all digits, the concatenation of all the digits, the concatenation of all the blocks of 2 digits. I call it first the mega block for length 1. Then I call it the mega block for length 2, when we have 0, 0, 0, 1, 0, 2, up to 98, 99. Then the concatenation of all blocks of length 3, starting with 000, then 001, up to 999. So this is the sequence we shall have in mind for a while. And Champernow, what he does is he counts how many times each digit appears in a mega block, how many times each block of 2 digits appears inside a mega block, how many times each block of n digits appears in a mega block, using the combinatorial elements that I mentioned that also Barbier used. It is, what are the difficulties? Well, the difficulties that he actually overcomes successfully is first that there are overlapping blocks. So here you have the concatenation of all blocks of length 3. And in pink, I put 3 occurrences of the block 000. One occurrence appears at the beginning of the block. The second occurrence appears in between the first and the second block. And the third occurrence appears in the last digit of the first block and the 2 first digits of the second block. So what does Champernow do? He does something clever, which is he only considers occurrences inside what he calls a block. And he ignores all the occurrences that appear in between 2 blocks. So those occurrences, he actually bounds them, and he's going to ignore them. So all of them, for his purposes, are going to be not too many, hence he can forget about them. So he bounds those and only considers occurrences inside what he calls blocks. And then the other difficulty is that for the proof of normality, he needs to count up to an arbitrary position within a mega block. So here I'm putting my attention, say, in a mega block of for length 2, and I want to know how many times number 7 appears inside the mega block in an arbitrary position. And in order to compute that, he actually needs to use the lexicographical order. And the computations are not hard, but they are delicate because you have to be careful how many times you have used number 7, that it may appear as a unit or as being in the middle of the block, not at the end of the block, or in the second position or in the first position, etc. So this is all I'm going to say about Champernowne's proof. And I'm going to tell you how we found a way to prove Champernowne's result. This is our observation. For simplicity, instead of using the alphabet of 10 symbols, I'm going to use the alphabet of zeros and ones, only 2 symbols. And our observation is that in the mega block for length n, if you view it circularly as a necklace, each block of length n occurs exactly n times at different positions modulo n. Let's see. Here is a mega block for length 2. So the mega block consists of all blocks of length 2 in lexicographical order. So 0, 0, 0, 1, 1, 0, 1, 1. The first occurrence of 0, 0 appears in position 1. So I'm going to label the positions with 1, 2, 3, up to 8, because there are 8 many digits. So block 0, 0 occurs first time in position, starts in position 1. Second time starts in position 2. Then let's go to 0, 1 appears first time in position 3, second time in position 6. 1, 0 occurs also twice, once in position 3, and now I'm in 1, 0, sorry. Once in position 5, and the other one you have to see it circularly in position 8. So it consists of the last digit in the last block and the first digit in the first block. And finally, 1, 1 occurs also twice, once in position 4 and once in position 7. Well, the fact that I show you this is, well, this is an observation that happens for the concatenation of all blocks in lexicographical order when you are in alphabet 2 and you're taking length 2, okay? But is this general? Well, we tried also for length 3 and also in some other alphabets larger, and it actually, it is verified first experimentally that say if you consider here, I'm not going to do it all, but if you consider the mega block for length 3, so you concatenate all blocks of length 3 in lexicographical order, and you wonder, block 000, how many times it appears? It appears 3 times at different positions modulo 3. It does not matter how you label the positions, you know the total number of positions, and you decide that one position you call it 1, and the other ones you name them circularly. And then you consider those positions modulo 3, because 3 is the length of the block. And it happens that each block occurs 3 times at different positions modulo 3. Now, after all the tests, we wonder whether some other permutations inside the mega block. So is there another way to order the blocks of length n so that this property still holds? And the answer is no. For instance, let's go back to blocks of length 2, which is easier to handle. If you consider all the blocks of length 2, 0, 0, 0, 1, 1, 0, 1, 1, but not in lexicographical order, but in the order I'm putting here, 0, 0, 1, 0, 1, 1, 0, 1. So you have there all the blocks. However, 0, 0 appears only once, and 1, 1 appears only once. However, 0, 1 appears 3 times, and 1, 0 appears 3 times. Don't forget of the last occurrence that happens at the very end of the mega block and the first digit. So there it is false that every block occurs twice at different positions modulo 2. So we came up with the following definition. We did this work together with Alvarez, Ferrari, and Juchman, And we gave this definition of a necklace, which is a circular sequence over an alphabet of B symbols, and we call it NK perfect because it will be perfect for blocks of length n appearing k many times. So such a necklace is NK perfect if each block of length n occurs k many times at positions that are different modulo k for any convention of the starting point. It is easy to see that if you take k equals 1, this definition coincides with the classical De Broglie sequences, which says that each block occurs exactly once in a De Broglie sequence. The length of an NK perfect necklace is k times b to the n, because if there are b to the n many blocks of length n and you want them to appear k many times. So when you have a necklace, each position of this necklace, perfect NK perfect necklace, gives a rise to one occurrence of a block, and they have to satisfy this condition. Our first theorem is to actually prove that the concatenation of all blocks in lexicographical order corresponds exactly to what is an NN perfect necklace. Let's see. First, we need to identify all the blocks of length n over an alphabet of B symbols with the representation in base B of all the integers between 0 and b to the n minus 1. So you have them written, say, the natural numbers written 0 and b to the n minus 1 written in base B. And now the theorem says that every arithmetic sequence, 0r, 2r, up to b to the n minus 1 r, for any value r integer that is co-prime with the base B, with the alphabet size, yields a perfect necklace for blocks of length n with n many occurrences. So for instance, for r equals 1, we have the result we were looking for, which is the lexicographical order of blocks of length n is an NN perfect necklace. And how is this proved? For this, we need the following. We have to start with a map between blocks of length n that is a bijection that should be a cycle. That means that if you apply successive many times the map to a given block, you obtain all the blocks of length n without repetition until you have produced them all. So no application, you have a block, one application, you have another block, another application of the map, you have yet another block until you have all the blocks of length n. Now that you have such a map, pick any block and make the concatenation of all the blocks that are obtainable by successive applications of the map. So this is sigma, which is the map to the 0, means no application of the map, concatenated with one application of the map. There's another block concatenated with the last block obtainable by a successive application of the map. And we say that, interpret that as a necklace, namely think of it circularly. That necklace is NN perfect, means that all blocks of length n will occur exactly n many times at different positions modulo n. If and only if it happens for this map, a very peculiar property means that if you give me a block that I painted here in pink, you choose the block, a pink block, and you split it in two parts. Does not matter the size. For any way of splitting that pink block in two parts, there should be one only possible way to fit that splitted block in the cycle. This means the first part of the split should correspond to the tail of one of the blocks in the cycle, and the second part of the split should correspond to the head of the next block in the cycle. And this matching should be unique. If this happens, then we are guaranteed that the cycle we started with gives rise to a nested, an NN perfect necklace, a necklace that is perfect for blocks of length n and n occurrences. I'm not giving all the details, but this is the core of the proof. It's a condition on a cycle. So this explains why the example I gave before for a concatenation of blocks of length 2 that were not in the lexicographical order failed to be perfect, because it failed this condition I'm showing here in this lemma. Well, now that we have a proof that every arithmetic progression yields a perfect necklace, we wonder whether there are more, or those are the only ones. And for this, we need the following graph. We call it an astute graph. It is astute because it allows us to prove what we wanted. So fix an alphabet of B symbols and a graph that we call astute for blocks of length n and k many occurrences is a directed graph with k times b to the n many vertices. Each vertex is a pair. It consists of a block of length n and a number between 0 and k minus 1, which will identify the type of position that block is sitting when traversing the graph. And there is an edge between two vertices when it happens that for the block in the first vertex, the last n-1 symbols of that block coincide with the first n-1 symbols of the block in the second vertex. And the number m in the first vertex plus 1 modulo k is exactly the value m prime. So here is a picture of how it looks, the graph for the alphabet of 2 symbols and blocks of length 2 and 2 kinds of positions or occurrences. Here then, since there are 4 blocks of length 2, 0, 0, 0, 1, 1, 0, 1, 1, and each of them come with a number 0 or 1 because since the value k equals to 2, then there are 2 possibilities. Either this companion number is 0 or the companion number is 1. And then since there are 4 blocks of length 2 and there are 2 possible values for the companion number, then this means that there are in total 8 vertices. And as there is something in this drawing that does not appear in the definition. The color of the vertices does not appear in the definition. I put it myself. It was only to identify easily, visually, the blocks that have a companion number being 0. And the other thing that does not appear in the definition is these labels that the arrows have. And this is a way to help to read the graph. It's only, it is implicit in the definition of the graph, but the color is implicit because I'm painting those that have a 0 as a companion. And also it is implicit this little number that appears by each of the edges. And it tells that if you have a block like 1, 0, and you consider the arrow that has a label 1, you go to another vertex that will have the last symbol of the first vertex, namely 0, followed by the number in the label of the edge, namely 1. So the block you arrive to is 0, 1. And the arrows link vertices of different colors. This means if you are this block is in a position that is labeled with a 1, then it will, by adding 1 more symbol, it arrives to another block that it is in a position that is labeled with a 0. So the arrows alternate the colors. So from a vertex that has white color, you arrive to a vertex that has a blue color, and conversely. First observation is that these graphs, if you take k equals 1, namely you consider only one type of positions, you obtain the classical de Bruijn graphs for blocks of length n over an alphabet of B symbols. The other observation is that this graph, Astute graph, admits an Eulerian cycle. This means that you can traverse the full graph using exactly all the edges once without disconnecting the traversal path. And this is useful because if you follow one cycle, then what do you obtain? As expected, you obtain that each Eulerian cycle in the Astute graph for blocks of length n-1 and k many symbols gives rise to one perfect necklace for blocks of length n and k many occurrences. Observe that there is a shift. The graph for blocks of length n-1 gives you one perfect necklace for blocks of length n. And this is very natural for those who are used to the Bruijn graphs, where there is a connection between Eulerian cycles and Hamiltonian cycles in the line graph. For those who are not familiar with that, this may look special, but it is correct. There is no mistake in the slide. The converse is not so easy because each NK perfect necklace can come from many Eulerian cycles at the same time. And the reason is that an Eulerian cycle may have a period inside. So the connection between perfect necklaces and Eulerian cycles requires that one makes a quotient by those Eulerian cycles that represent the same necklace, which is to understand all these periods inside. So we can actually count how many NK perfect necklaces over an alphabet of P symbols there are. And I'm not going to explain the formula, but Euler's totient function appears in this formula because you have to get rid of these, as I said, periods. So there's a subtlety there. But other than that, essentially, Eulerian cycles in these Astute graphs corresponds to NK perfect necklaces. Now that we know that there are a lot of perfect necklaces, we can actually prove the wanted theorem, more general than initially thought, which is that the concatenation of NK perfect necklaces over an alphabet of P symbols for NK increasing at most arithmetical, you cannot increase too much, is normal to the alphabet of P symbols. This means that you start with, say, a 1-1 perfect necklace, you concatenate with a 2-2 perfect necklace, you concatenate with a 3-3 perfect necklace. So you can use n perfect necklaces, or if wanted, K can be smaller or larger than n, and still will be true. This theorem was first proved by Edgardo Ugalde, a Mexican scientist, for the case of k equals 1 for the Bruijn sequences. And the proof is not similar to the one I'm going to show you here, but the reason for this to be true was first found by him. And this is the standard, a comment on what it would be the standard proof that I'm going to show you another way. But suppose you want to do it as the definition tells, that we know that the number is normal to base B if in its base B expansion, every block of digits occurs with the same limiting frequency as every other block of the same length. This limiting frequency is in pink because I want to stress that we have to take the proportion of times each block appears in an initial segment of our construction and take that proportion of what happens in the limit. Even though the result of normality is a property that occurs in the limit, one must bound or have complete control of the number of occurrences or the proportion of occurrences of each block at any arbitrary position, say where the arrow is pointing. You need to know how many times a given block appears up to any arbitrary position you want. And you need to bound that because you need to prove that the limit of the proportion of occurrences goes to what is expected to be. So usually you need to bound or know exactly how many times each block of digits occurs at any arbitrary position. And this makes the constructions, it is normally not the most difficult part. You come up with a construction and then you have to count how many times a block appears at any particular position. What I'm going to show you now is that with a seemingly simpler formulation of normality, one can give the proof very elegant and without all those difficult computations. And it is based on a lemma or a theorem proved by Piatetsky-Shapiro 1951, that instead of computing a limit, it computes the lim sup. It says, oh, don't worry, you don't need to know the limit. It suffices that you can bound the lim sup, but for all blocks, you have to bound their proportion of occurrences with the same positive constant. The fact that it is the same positive constant, it is really doing the job that indeed you can prove the equivalent, that this is an equivalent formulation of normality, but it is simpler to test. Let's see. The lemma says, a sequence, I'm putting directly the digits, a sequence of digits, A1, A2, A3, etc., digits in an alphabet of these symbols, is normal to that alphabet if and only if there is one positive constant such that for every block, the lim sup of the proportion of times that this block appears in is smaller than that constant times the expected frequency. So this is really much better to test than actual counting, because instead of counting how many times a given block occurs in a position where the arrow is in my little drawing there, you can bound the number of times a block appears by counting directly how many times it appears at the end of the mega block. And you know how many times a block appears at the end of the mega block because the mega block have been used, are exactly NK perfect necklaces in our case, and we will know how many times each block will occur, not only inside the block, but in between the positions of internal, in between blocks. Is this clear? I hope so. This lemma is very convenient. It helps to prove many known constructions, and then it becomes a much simpler. And I put here a square because this is all I'm going to say for explaining why the concatenation of NK perfect necklaces is indeed normal. Because thanks to this lim sup, and thanks to the fact that these NK perfect necklaces only increase arithmetically, so the length is not that large, so there will be no fluctuations in the number of occurrences internally. The lim sup ensures that it will be actually the case that the sequence done in that way is normal. Now we come to our problem back, and we know that the concatenation of n perfect necklaces for n linearly increasing is normal, which is how Champernot started his proof. And now to finish the proof, we apply the same modification that Champernot did in his article, and we obtained his result. I'm not going to explain that modification. It's simple, but since it is exactly the same as he did, I just leave it here. And already the concatenation of all blocks of the same length in lexicographical order is already an example of a normal number that you know how to prove. And this is the end of the first part of the talk. Now I would like to move to a special property of normal sequences. And for this, I would like to give the formulation of a normal number in terms of uniform distribution modulo 1. Proved by Wall in 1949, a real number x is normal to a base b if the sequence of the fractional parts of the actual number x, the number b times x, the number b squared x, that is the sequence formed by b to the n times x modulo 1. This is taking the mantissa of x, removing the first digit, then removing the second digit, then removing the third, the initials, the prefix of length 1, then you remove the prefix of length 2, then remove the prefix of length 3. And for that sequence, you ask that it is uniformly distributed in the unit interval. Now, what does it mean to be uniformly distributed in the unit interval? Means that if you choose an interval, a subinterval of 0, 1, and you take an initial segment of this sequence large enough, the proportion of elements that will be in the interval has to be essentially equal to the length of the interval. So if that happens, the sequence is uniformly distributed. It is possible to formalize the notion of a uniform distribution using the function called discrepancy. The discrepancy is it is a function that takes n many terms of the sequence, and its value is the supremum of what happens in every interval of this interval 0, 1. And it says that a sequence is uniformly distributed if this discrepancy goes to 0 when n goes to infinity, when you take bigger and bigger initial segments. And what does the discrepancy say? The discrepancy is the difference between it's a supremum of what happens in every interval alpha beta, and you ask for the proportion of elements in the interval alpha beta, and you subtract the length of the interval, and this difference, taking absolute value, is the discrepancy. Can the discrepancy be 0 for some sequences? No, it is impossible that the discrepancy be 0. There is a minimum value of the discrepancy. This is a very celebrated result by Schmidt in 1972. Many people, including Roth, work on this problem of finding the minimal discrepancy that holds for every sequence. So actually the result says that there is a constant such that for every possible sequence, no matter which sequence, there will be infinitely many n's where the discrepancy is above log n over n. And this is celebrated because Schmidt's result is optimal, because there are some sequences that have exactly this discrepancy, not as a lower bound, but exactly that. But this is for all possible sequences. What happens with our sequences, the one we want? Our sequences are of the form b to the n times x modulo 1. So these are all the mantissas of a given real number. And there it is not known whether this lower bound is as such or it is larger. Of course, that is a lower bound, but is it optimal? And this question was asked many years ago, 1956, by Korobov. The best result in that direction is the construction done by Mordechai Levin, that he constructed one real number such that the discrepancy of the sequence b to the n times x modulo 1 is a logarithmic factor above the optimal discrepancy obtained for the bigger class of all sequences. And he used a method that I will not explain here. Instead, what I'm going to do is explain you Mordechai Levin's construction in terms of perfect necklaces. And we are very happy about this understanding that we obtained. For this, we need a definition, which is a nested perfect necklace. Suppose you have an alphabet of B symbols. We say that a circular sequence is a nested NK perfect necklace, namely a perfect necklace that is nested for blocks of length n and k many occurrences. If it is indeed an NK perfect necklace, and in case n is greater than 1, this necklace is a concatenation of B many n-1 k perfect necklaces. So for instance, if you consider the alphabet of 2 symbols, the following is a nested 2 perfect necklaces. So we are going to consider blocks of length 2 occurring twice. So here's 0, 0, 1, 1, 0, 1, 1, 0. The 4 blocks of length 2 appear. This is not the lexicographical order. And why is it? Because each block of length 2 occurs twice. Here, the first time for 0, 0 is in the first position. The second time, it is understood circularly. The last digit concatenated with the first digit. 0, 1 appears twice at different positions, even and odd positions. 1, 0 appears twice, and 1, 1 appears twice. Moreover, now we have to see that it is nested. And it is nested because if you split it in 2, the space I put in between it was to facilitate the reading of 2 parts. And the first part is a 1, 2 perfect necklace. That means all blocks of length 1 appears twice. So blocks of length 1 are exactly the digit. Digit 0 appears twice, digit 1 appears twice. Same thing in the other half. Digit 0 appears twice, digit 1 appears twice. Now, the lexicographical order of blocks is a 2 perfect necklace, yes, but it is not nested. Here it is 0, 0, 0, 1, 1, 0, 1, 1. We know it is perfect, but it is not nested perfect, because if you split it in 2, then the first part is not a 1, 2 perfect, because digit 0 appears 3 times and digit 1 appears just once. So it is important to remark that nested NK perfect necklaces are pointed. That means you have to understand them circularly, but they have an initial position. And this is crucial because you need to split it in 2 in order to test whether the left part and the right part is, again, nested for the lower length of the block. So they are pointed, they have an initial position. You cannot rotate anyway. There are some possible rotations, but really in the way we write it, we have to keep it. This is just to show that it is possible to construct more. These are 2 4 perfect necklaces, meaning perfect necklaces where all blocks of length 2 appear 4 times at different positions modulo 4. And if you concatenate the first 2, you obtain a 3 4 perfect necklace. The same happens if you concatenate the second 2, you obtain a 3 4 perfect necklace. And if you concatenate them all, you obtain a 4 4 perfect necklace. Now that we know how to construct some, I will make a very easy observation that will, I expect with this observation to lead you to understand why a construction based on nested perfect necklace is going to have such a low discrepancy, which means it's going to converge to the property of normality very fast. All occurrences of any given block will be satisfied as expected very soon. The observation is as follows. Again, assume an alphabet of B symbols and suppose X is an NN perfect necklace. Since it is NN perfect, each block of length N occurs N many times in X at different positions modulo N. But since it is nested, and this is a picture, it happens that for any block size, let's call the block size I, the necklace X can be understood and it is the concatenation of B to the n minus I nested IN perfect necklaces. So if you take a prefix of your construction, or of your, if you take a prefix of your NN perfect necklace, which is nested, and you take exactly a prefix that is multiple to the size of a IN perfect necklace, then what you're going to find is that in that prefix, each block of length I occurs as many times as the number of I perfect necklaces that fit in. And n times, as many times as that, because it is indeed the concatenation of B to the n minus I nested IN perfect necklaces. There is a little variation, or there's an epsilon appearing there, you can ignore, and it has to do with the fact that the necklaces should be understood circularly, and if you're taking a prefix, you are breaking the circularity that was expected at the moment you constructed the object, but you can ignore that. So the first theorem in this direction says that the binary expansion defined by Levin using the Pascal triangle matrix modulo 1, that I have not explained how it is used to construct it, but his construction is actually the concatenation of nested 2 to the D, 2 to the D perfect necklaces. So the necklaces increase geometrically. And here's a picture of how I see they are nested perfect necklaces 1, 1, 2, 2, 4, 4, 8, 8. So they increase geometrically. This explains that triptychal construction in a very combinatorial way, which is, as I said. And making a variation of his method, it is possible to construct many of these objects, and we actually counted this 2 to the D minus 1 binary nested 2 to the D, 2 to the D perfect necklaces by a variation of his method. So now we know how to make many. And why is it the case that they have the property of converging to normality so fast? Or another way to say this is that the discrepancy of the sequence 2 to the n times x, where x is the real number corresponding to the sequence we have just constructed, has low discrepancy. And the reason is in this lemma. Imagine, I'm going to read better the picture. Imagine you have your construction that says you have a nested n perfect necklace followed by a nested 2n, 2n perfect necklaces. So we increase the parameter by 2. And now you wonder, if you take any segment of the length of an n perfect necklace, how many times you will find a block of length n? If that segment matches exactly the n perfect necklace, you know every block appears n many times at different positions modulo n. The other position is that this block that has the size of an n perfect necklace is in between the two nested perfect necklace we have, the one n perfect and the 2n to n perfect. So I painted it here in blue. And you wonder, is it still the case that each block occurs, each block of length n occurs n many times, even though I'm sitting part of it inside of the bigger perfect necklace? And the very important property for this construction is that indeed, yes, it's going to happen that each block of length n occurs n many times inside the blue part too. The reason to explain this, yes, it has to do with the method itself, that it uses Pascal triangle matrix modulo 1. And for another block size, also another block also of the size of an n perfect necklace, and now I painted in pink, it will, sitting inside the bigger 2n to n perfect necklace, it will also happen that each block of length n will occur exactly n many times plus minus epsilon. And for that reason, the idea, I'm going to sketch it here. I hope you follow me, but if you miss this part, it's not terrible. The leading idea is easier to see when you take an alphabet of 2 symbols, and it has to do with the recursive nature of the construction. A nested 2n to n perfect necklace is equal to 2 nested 2n minus 1 to n perfect necklaces, which is equal to 4 nested 2n minus 2 to n perfect necklaces, which is equal to 2n nested n to n perfect necklaces, which indeed are equal to the double, 2 to the n plus 1 nested n minus 1 to n perfect necklaces. Now that you have these objects that are made of blocks of length n minus 1, you know that each of them appear 2n many times, but half of the time have to be followed by a 0 and half of the time have to be followed by a 1. That means that for each of those objects, you find that each block of length n will actually occur n many times. And this makes you believe that if you are sitting in a position that it is multiple to the size of a nested n perfect necklace, then the number of occurrences of blocks of length n inside the bigger nested 2n to n perfect necklace will be as expected. Well, with this in mind, we can actually arrive to this last theorem that I'm going to mention, which is that nested perfect necklaces are associated with the low discrepancy. And it says that if you are in a base B, which is a prime number, so we don't only have it for base 2, but also for primes. Every number x whose base B expansion is a concatenation of nested 2 to the d, 2 to the d perfect necklaces for d equals 0, 1, 2, will satisfy that the discrepancy associated to the sequence b to the n times x modulo 1 is as low as I mentioned at the beginning of the talk, namely log n squared over n, which is a logarithmic factor above the lowest possible discrepancy known for sequences. And there is no known sequence with lower discrepancy that's lower than this. We could not obtain this theorem for arbitrary numbers that are not prime. And this is the end of the second part of the talk. And I would like to mention 3 open problems. One is that we still do not have a graph interpretation of nested perfect necklaces. The graph interpretation is for perfect necklaces in the Astute graph as Eulerian cycles in the Astute graph, as I showed. But when you add this recursive condition of being nested, we don't have a graph interpretation anymore. And we really want to have that. Another problem is to study perfect necklaces and eventually nested ones in higher dimension in the torus, as it has been done for de Broglie sequences. And we believe there is a lot of interesting problems appearing in higher dimensions. And the last question, as I promised, is related to Martin law of random real numbers. And the question is whether there exists a Martin law of random real with the low discrepancy that we can obtain by our construction, or Levin obtains by his construction, namely the discrepancy associated to the number x being real of the sequence 2 to the n times x modulo 1. This question, I truly believe it is false, that there is none, because it is known that almost all numbers have the sequence associated to almost all real numbers have a discrepancy in the order of of the law of iterated logarithm, square root of log n over n, which is much larger than this. So this is quite an exceptional property for a real number. So we expect that there will be a Martin-Love test collecting all the numbers whose sequences have a discrepancy larger than this, or a discrepancy below what happens for almost all real numbers. But still that proof has not it's unknown. But imagine you prove that there is no Martin-Löf real number with this low discrepancy. The question is, what is the discrepancy of the set of Martin-Löf real numbers? Where does it sit? And this is something that people doing uniform distribution do care. So it is a study of different kind of sequences. And these kind of sequences play some role in their theory, the sequences of shifts of a mantissa or 2 to the n times x modulo 1. Well, this is all I had to say for today.
Thank you very much. Veronica, are there questions?
Can I ask one?
Go for it.
So in your last question, do you know if it's known for n random, for any n? Instead of one random, n random.
No. I think in those cases, all those are going to be measure 1, and this is an exceptional property, would be out. But eventually,
Yeah, but do you know which n is it out at?
That's right. We need a proof.
Okay, so you don't know anything.
No. The only thing I know is a paper by Gal and Gal. I have not put it in the references here, but it's a paper that proves that almost all numbers are have a discrepancy which is larger than this. So it gives a bound, and it constructs a set of measure 0 for that. So eventually one can effectivize the items appearing in that proof and put them into a Martin-Löf test. But details to come.
Thanks. Peter Boss, you have your hand up.
Yes. Can you hear me?
Yes.
Somewhere in the middle of the talk, you used this lemma, showing that in order to prove that the average number of the iterates is indeed equal for all. I think it's somewhere on slide number 18 or something like it. It was this lemma you.
18.
Yes.
18 here.
Yes.
Sorry.
Oh yes, there it is.
Yeah.
No. No, I think it was even before this one. Yes. This lemma of Piasecki-Shapiro. You have here constant C, but if you use it to prove normality, then as a corollary, you will have that C actually should become equal to 1 in this estimate, because it holds for all the blocks.
I don't see why it must be equal to 1. Many times you need you make use of this constant being larger. I have.
Yes, in the estimate it's larger, but if it then follows that this number is normal, you have equal distribution, and if it's always some, if it's it cannot be that this lim sub is either larger or smaller, because then the distribution isn't equal.
Yes, yeah, you're absolutely right. That's why I say that it is simpler to test, and it's a seemingly simpler formulation of normality, but it is an equivalent formulation of normality. So it is necessarily the case that this constant can be taken to be 1, because indeed what happens is that the limit of the number of occurrences is equal to the expected frequency, and this holds by equality. But for the lim sup, it suffices that you say, okay, I bound it with this larger number.
Okay, so it's observation holds. Thanks.
There are 2 examples of this proof in one writing I have on normal numbers and computer science. And there are two proofs that make use of this constant for well-known constructions, where it is very convenient to use it because it's okay, I bound the number of occurrences of each block by what happens at the end of the current mega block I'm looking at.
You can lose some inaccuracies in the estimate. I understand that.
Well,
thank you.
Thanks. Are there other questions? Okay. If not, let's thank Veronica again. And please stay on for a second because Maria has an announcement that you wanted to share with us. Do you want to do that?
Yeah. Hi, everyone. Can I share my screen?
It should work if you just do it. Yeah, because you're a co-host.
Okay. So I'd like to I use this opportunity to advertise mentorship program that the Women in Computability interest group, part of the CEO. This is a mentorship program that is, the goal is to bring together more experienced researchers with young researchers in our field, understood in the most broad way, as CIE does. Originally, we had such a mentorship program that operated during conferences, and mentors would meet up with young researchers and talk during coffee breaks. And the idea was to form a community and a support system this way. But this year has shown to us that there's no need for in-person interaction to have a successful program. So we've decided to move this program and online, and we have already a pretty nice list of mentors who've already agreed to be part of this. You can see more about this on the webpage. And I wanted to ask you to help me spread the word. If you're a woman mentor who would like to participate, please reach out to me. But if you're a young researcher, or if you have students who are young researchers and would like to use this opportunity to connect to another experienced person in our field, all you need to do is fill out this little application form that tells us a little bit about each person applying, that we can match them to the best possible mentor. Of course, the applicant can list their favorite choices, but we don't want to overburden specific mentors, so we'll have a uniform distribution. And yeah, we're hoping that this will help support the community. I'm gonna send you the link in the chat. Let's see. So that you have, there it is, the link to the webpage. So that's it. Thanks very much.
Great, thanks. Yeah. So I think we can at this point end the recording, and